So I've put the thing in, Dave, the YouTube link.
Okay. Can you see my slides screen?
Yep, we see random walks too. So I think the plan today is to do a little bit more with random walks, and depending on the time.
Can you see my slides screen?
Yep, whoops. Okay, and depending on the time, to also have a fun discussion on discrete versus continuous.
Was that me that had?
No, that was me. I killed it.
Okay. Can you see my slides, Steve?
Yep, we see random walk. Oh, there's another one. Sorry.
Great. So hi, everybody. Welcome back to another lecture in spring 2021 semester of computational thinking at MIT at 6 SO8318 S191. So as Alan said, today we're going to have the second lecture about random walks. So we actually had a small technical problem with the video of the last lecture, and so we have only just been able to actually upload that video to the YouTube channel. So if you're watching this, you probably want to actually look at the previous video first, although they're reasonably independent, at least to start with. Okay, so what are we going to see today? Well, we're going to talk more about random walks. And what we're going to see is that in Julia, let me just zoom in. If we have an object, we can actually define a way that we want to view that object. When we ask Julia, to just display the value of the object, we can actually customize how it does so, and we'll see that in action using structured matrices. So if you remember from a few lectures ago, we had various kinds of matrices with structure, by which we mean that we know where there are zeros in the matrix. And then it turns out that in Julia, if we actually, Julia has predefined types that represent such structured matrices, like lower triangular, for example. And when we display them, it will display them in a nice way. Then we'll see this function called cumsum, which does cumulative sums. And we'll see how we can do vectors which contain vectors inside them. So each element of the sort of outside vector is itself a vector. And then once we've constructed a vector of vectors, we often want to put them all together, and that's called concatenating them. And we do that with, for example, the hcat function, cat for concatenate. And also look at two ways we can draw plots in 3 dimensions. I think we've already mentioned these, which are heat map and surface both from the plots.jl package. Okay, so let's start off with a nice diversion, apparently, which will turn out to actually be related to what we've been talking about. So that's Pascal's triangle. So probably you saw Pascal's triangle at high school or sometime previously. And just to note that, of course, as usual, and I think it's Stigler's law that says that the person after whom a concept is named is never the person that actually discovered it. And indeed, Pascal was not the first person to study this triangle. It had already been studied centuries before in India, Persia, China, etc. And here's a link to the Wikipedia page, which has links to documents that show how it was being studied in other countries much before Pascal. But Pascal apparently did contribute a lot to the understanding of this triangle. So what is Pascal's triangle? So we can generate it in Julia. I've written a little function that takes in a number, capital N, and it generates this matrix that we're seeing here. And the way it does that is by calling this function called binomial, which generates what are called binomial coefficients. So what are the binomial coefficients? They're actually, you can think of them as the kth entry on the nth row is the coefficient of x to the k when you expand out 1 plus x to the power n. So, so we could actually do this symbolically in Julia, but maybe I don't have everything set up right now to do that. But if you think about, what is 1 plus x squared, I'm just going to expand out the brackets, and I'm going to get 1 plus 2x plus x squared. And so if you look at the coefficients of each power of x, you get 1 multiplying x to the power 0, which is 1, 2, and then 1. And that is exactly what we see on this row of the matrix, 1, 2, 1. And so, if we do 1 plus x cubed, we'll get 1 plus 3x squared plus x cubed. And so that's where these numbers come from. That's one place they come from. And this is called a binomial. It has 2 terms. That's what binomial means. And so these coefficients that we get when we expand this product of all of these things, what are we actually calculating? You can think of writing this out. I write that out as 1 plus x times 1 plus x. What am I actually doing? I'm just choosing one of these two objects from each set of parentheses. And so the coefficient is actually the number of ways that I can choose, you know, 1, 1, and 1x. The number of ways I can choose that is, well, I choose a 1 from the first bracket and an x from the second, or an x from the first bracket and a 1 from the second. So there are 2 ways of doing that, and that's what this coefficient is. And so there's this function binomial to calculate that in Julia. What is that actually doing? There's a formula for that in terms of factorials, and you can write that out. And as usual, you know, if we wanted to know exactly how Julia was calculating it, we could do sort of edit binomial of 1, 2, or whatever, and it would take us to the source code. And you can look at exactly how it's implemented, which we won't do right now, but feel free to do it yourself. Okay, so note that in this matrix, because of the way these binomial coefficients are defined, it does not actually make sense to talk about n binomial of nk, also called n choose k. It doesn't make sense to talk about that, at least in this interpretation, as coefficients for k bigger than n. And so it just fills all of those elements with 0. If you look at this matrix, it's actually kind of difficult to visually notice that all of those elements are 0. So actually you would kind of want to, there's too much visual noise. Those zeros are too, you know, it's difficult to pick out which are zeros and which are not zeros. And so we might want a different representation of that matrix. And so if you notice this matrix, the coefficients that we're interested in are actually on the lower half of the matrix. Basically, they're on the diagonal and below the diagonal. And so this matrix is actually what we call a lower triangular matrix. And Julia has a type called lower triangular, which we can apply to this matrix that I generated, which is coming from this Pascal function I wrote. So I'm passing in 10, that's the size of the matrix, 10 by 10. And now I'm passing it into this lower triangular constructor. So this is a new type called lower triangular, which therefore has a constructor, and I can pass in the data I want to put in that type, an object of that type. And we see that when I do that, it displays it in a nicer way, so that these zeros have now just become dots. And so this is an example of a type that's defined in Julia where we actually can tell, decide how to display objects of this type. And so the way we would do that is actually, we do this by extending the show function from base. There's a function called show in base Julia, and we would extend that by doing something like, so let's make a new type called my type, which has an int inside. And then we're going to do base.show. And I need this IO object, which is input output, and an object X of my type. How am I going to display that? I'm going to put something like, I'm going to print to that output stream, this is my type with value. The value I'm going to interpolate into that string of X. So maybe let's not call it X, maybe we'll call it hello. Let's just call it hello. Hello.x. So the value of X inside the hello object, close the string, and then if I make an object of that type, let's call that Y. Sorry. I'm going to make an object of that type by calling the constructor that Julia automatically provides. My type of 10, and it will print, should display Y equals, this is my type with value 10. So that's basically what they're doing. So when you generate this lower triangular type, it prints out the size of the matrix, and it tells us that it's lower triangular, and these are the types of the objects inside. So int64 means that the elements of this lower triangular matrix are of type int64, and matrix int64, even though it's duplicating and repeating this int64, it just means that the underlying data that is being fed into this lower triangular object comes from a matrix with int64 inside. Okay, so these are called type parameters, and we've seen that a bit before. So yeah, so what's happening here is that, because I'm telling it that Julia, that this is a lower triangular matrix, it actually knows that these zeros are what are called structural zeros. They are zeros that we know are in those positions in the matrix because we know somebody told us that this matrix is lower triangular. And lower triangular matrices occur in various important algorithms in computer science. And because of the way the algorithm works, for example, Gaussian elimination, you know that the result of this algorithm will be a matrix of this type. And so you know that there are going to be zeros there, and then we can use that later on to, for example, solve a linear system with this matrix in a simple way. Okay, so another structured matrix representation is a sparse matrices. We've already seen those in a previous lecture. And when we display those in Julia 1.6, the display has actually changed. If you remember, before we saw that basically when you tried to print out this matrix, it would give you a list of positions I, j with their associated values. But that has actually changed in Julia 1.6 to make it nicer to visualize. Now you see them printed out in this way, just like with the lower triangular matrix, with these dots representing structural zeros that we know are zero because of this.
I love that change, because whenever I just saw that list of IJ and AIJ, it never meant much to me.
Yeah, that was exactly that. You know, it was pretty difficult to get to understand the structure of the matrix like that. But the point about sparse matrices is actually, you know, they really become interesting when the matrix is big. And so let's, for fun, look at bigger matrices from Pascal's triangle. And what we're going to look at is actually where the elements of Pascal's triangle are odd numbers. So if you look at this table, you'll see that there are some odd numbers like these 5s and these 15s, but there are also a lot of even numbers. And so the question is just, what is the pattern of odd and even? And that turns out to be actually rather interesting. So let's do that. So here I'm printing out the sparse matrix that I'm getting from Pascal with this size, right? So here's a
I think it's one more than the size.
Yeah, right. So Pascal's triangle starts at row 0 and column 0. And so here I've actually got, I'm numbering starting at 0, basically. Okay, so as I increase the size, well, we see that indeed the matrix grows. But at some particular point, you see at 16, it decides, oh, that's getting too big. And since I have a sparse matrix that I want to visualize, it actually gives me a much more compressed representation. So this is called the sparsity pattern of the matrix. And now the dots actually are meaning the non-zero elements. Right? So the 0 elements are now just displayed as blank space. And what you notice is that this pattern of odd elements is actually rather interesting. And when I keep increasing the size of the matrix, you get this amazingly intricate pattern, which you might know is called Sierpinski's triangle, or a sort of squashed version of Sierpinski's triangle. And so why is this happening? That's a much more complicated question that we're not going to go into, but it's just nice to observe that Julia is actually showing us this in a very nice way that's actually giving us much more information than if we just saw the numbers printed out with all those zeros.
I think there's also sort of a simple but big point that I think people sometimes miss, which is that when something gets very, very large, you really sometimes want to lose information to make it understandable. I mean, like, you go to something like Google Maps, right? When you go outward, you don't have the street level detail anymore, right? It disappears. I mean, we've all seen that, right? And then the county level, the state level disappears as you go out further, right? And then when you zoom in, you get more levels of detail. So, one might think that, oh, well, when you zoom out, you should just keep everything, because who wants to lose information? But it's always somehow better that, like, when you go outward, like, less is more. It's such an obvious thing, but, we don't always remember to sort of portray things that way.
Yeah, thanks. Good one. Okay, so by the way, there is an alternative way to look at Pascal's triangle with just sort of change the variables, and then it actually rotates it. So you now get Pascal's triangle rows on the diagonal of this matrix, and it sort of looks more symmetrical in this representation, maybe. And yeah, thanks. And exactly, those are the rows of Pascal's triangle in the way that we are used to seeing them, and if it's basically symmetrical now with respect to the y equals x sort of diagonal line. And actually, this new version can be produced from the previous version by doing this particular matrix multiplication of the original Pascal triangle in the lower tridiagonal form, and then you transpose that. That's what this prime means it means transpose, it's a flip rows and columns, and this is an upper triangular version of the Pascal, same Pascal triangle, and then we do matrix multiplication between those, and we actually get back this same version of the matrix.
That's when you thought you knew everything about Pascal's triangle, new fun things come along.
Right. And so, okay, so how do we actually get Pascal? Where does Pascal's triangle actually come from? So, you know, we were using these binomial coefficients, but you know, you probably didn't learn Pascal's triangle like that when you were at school. Rather, you learn how to build up the rows. So if we look at, you know, this smaller version, let's remember, how do we build up this 1, 2, 1 row? Well, where does this 2 come from? It comes from adding this 1 that's just above it with this 1 that's to the left of that 1. So it's sort of adding the north to the northwest you know, component at each time. And that's true for each of these thanks. For each of these things. I was going to draw that out, but I didn't decided not to do it. But yeah, it's easier to do just by sketching by hand. And so, well, if we think about it, sorry, so you start with this initial row with just 1, 1 and all zeros, and then you just follow this rule and you construct all these next rows. One by one, you construct the rows. And so, so if we think about how we would actually do that in a program, what would we do? We would literally start with a vector, and then we would apply this rule to get the next vector. The rule that I just said is adding the upstairs and left-hand elements. So what is that rule actually? Well, if you think about it, what we're doing is multiplying this number by 1 and adding this number multiplied by 1, adding those together to get the next one. And that is exactly a convolution. So we've seen convolutions come up several times, and here's another example of a convolution. Let's remember that basically we're thinking of convolutions as some kind of local operation, local meaning that it only deals with a neighborhood of your current point, but we're doing the same operation on the neighborhood of each point, right? So we're doing exactly the same kind of thing to each element of this vector, and the output is the output of applying that little local operation to each element in turn. And
so hopefully people might remember the pixelated Mario, which was a 2-dimensional convolution.
Right.
And there was like that little 3x3 window that moved along the pixelated Mario. Well, now we're kind of in 1 dimension. And so it's not like it's not a 3x3. It's just, well, in this case, it's just a 2, right? It's the 2 numbers 1, 1, which slide along any one row of this matrix and produce the next row of this matrix.
Yeah. Yeah, so it's kind of like an image filter, except we're applying it in a different way now, because we're now you know, taking the result of the first operation and making that the new next column, and then we're taking the result of that operation and applying the convolution again. So this is actually a new application of convolutions where we repeatedly apply the same convolution operation on the output of what we just got. And when we do that, we build up literally the same matrix that we had before. Okay, so what does this have to do with random walks? Well, this is almost exactly what a random walk does. So let's, a particular random walk. So let's look at that. So let's remind ourselves what a random walk is. So, you know, so what is a random walk? It's just you start somewhere and you move the simple random walk in 1 dimension. You start at 0, for example, and at each step, each time click of a clock, you move left to -1, or you add -1 to your current position. You jump by a distance -1 with probability 1/2, and you jump right with probability 1/2. And then you keep doing that, right? Just like we kept doing something to Pascal's triangle, just now we keep adding random steps to wherever we just got to. And so, okay, so those random jumps we can think of as random variables, as we discussed a couple of lectures ago. Each step is a random variable, which has, as I said, you know, the outcome -1 with probability 1/2, and the outcome +1 with probability 1/2. And so every time I generate a new copy of that random variable that is very similar, related to a Bernoulli random variable, every time I do that, I will get a different answer. I'll either get +1 or -1 randomly, and when I do some probability distribution with a histogram, I should see that approximately half of the time I get +1 and half of the time I get -1. But now that's what we've already covered before. But now random walks, what do? They take that random variable, and now they do it a lot of times. And then to each, when they have all of those different random variables, we're now going to add up the outcomes of all of those random variables to make the value of the random walk, the position of the random walk at time n. So at time n, we'll add up n of these jumps to get the position at time n of the random walk, or rather the displacement, right? So we could start somewhere that's not exactly at 0 at the initial position. And so the random walk is, you can think of it as actually the displacement at time n, the distance from the origin. And so if you think about it, often what we do is we have that each of these steps is actually independent of the previous step. And so if I take a random step at time 10, and then the next step at time 11 should not depend on which choice I made at time 10. There are other kinds of random walks that are more complicated where that choice will depend on something, but we're not going to talk about those. And so basically what we have is that each step has the same distribution, the same chance of jumping left or right, and it's independent of all the others. So this is the very common case in probability theory, which is called the case of independent and identically distributed random variables. So it says what it is.
I always thought that was a very long term for.
Yeah, it is a very long term, and that's why it's often abbreviated as IID, independent and identically distributed.
Yeah, for just do the same thing without any link between them.
Yeah, you're exactly. Repeat the same thing over and over again, and they're all independent. But then for a random walk, we want to take all of those IID, independent, identically distributed random variables, and do something with them. We're going to add them all up. And so what do we get? We get something like this. So if xi is the name that we're giving to the ith step, that's a random variable. Then x1 is the random variable corresponding to the first step with this particular jump probability distribution. X2 at the second step, etc., and xn at the nth step. Then the sum of all of those is the position of the random walk at time n. It's just the sum of those random variables, which you could write with a sigma notation. And so again, what we mean by the sum, we mean a new random variable, whose outcomes are the sums of the outcomes of the random variables that we put in, and the probabilities behave in a particular way that we're going to cover in homework. Okay, so but there's a key point about a random walk, which is that once we've got the result at time n, we also want the result at time n plus 1. And how do we get that? We take the sum of these x's all the way up to time n plus 1. And that is supposed to be actually the position at time n plus the nth and the step at time n plus 1. And so if you think about it, although the x's are independent, are mutually independent or independent of each other, of one another, the s's, the distances, the positions at time n are not. Right, so if the position, if you happen to have a path, a random walk path, trajectory that goes very far in time 100, then at time 101, the position will still be very far away. They're correlated, and so they're no longer independent. And so that makes it actually harder to generate samples from this object. It's a more complicated object because actually what we need is indeed what's called the whole trajectory of this random walk, which is the sequence of positions at each time step. And those are given by partial sums like this, right? So the position at time 1, we're thinking of just random walks that start at position 0. Then the position at time 1 is just given by the outcome of the first jump. But the position at time 2 is the outcome of the first jump, the same outcome, plus the outcome at the second jump. And then at the time 3, it's the sum of those first two that we already recorded. That's the point, right? We're basically sort of recording these in order, and we are just the recorded value is going to be the previous value plus whatever the random outcome at the nth step was. And so we're recording those in order, and then we need to sum them all up in this way. And this process is called a cumulative sum. So here's an example with numbers. here are my random steps plus or minus 1 in the same way that we've been doing all along. And now I want to add those up in this way, right? So the first result is going to be -1. Then the second result is going to be -1 plus 1, which is 0. Then the third one will be -1 plus 1 plus 1, which is 1, etc. So that is what this CumSum function does in Julia. So CumSum of this vector of steps indeed goes -1, 0, 1, just like I did by hand. And then it carries on and gets all of the results, which are these partial sums. And that's called a cumulative sum or prefix sum or scan, probably has some other names. Okay, and you can do this with this CumSum function. So here's another example, 1, 2, 3, 4. The CumSum is 1, 3, 6, 10, which you might recognize as the triangular numbers.
So I noticed the trajectory doesn't, it doesn't have the 0 step, so to speak.
Right, so yeah, exactly. Yeah, so okay, that's true. I should have put that in. Yeah. So you can do that by, so instead of just CumSum of steps, we want to make a new vector where we start with 0, and then we're going to concatenate that 0. That's what this semicolon does. I'm making an array with these square brackets, and then I'm concatenating that whatever is before the semicolon with whatever is after, and then that gives me the whole random walk trajectory. So it has one more entry in the vector than the number of steps. Yeah.
So this is also like if I had a bank account and every day I either added or withdrew $1 and I'm allowed to go negative, which some bank accounts let you do. And this is the graph of my balance on each and every day.
Yeah, that's a great analogy. Yeah, so yes, here's just plotting that vector in time, and you can see that indeed it's doing the random walk. So just to note that if you've come from some other languages, especially things like Python, R, or MATLAB, and you had simulated random walks there, you probably would have been told to use CumSum, and that you should not do it, for example, with a for loop. But in Julia, and that's because CumSum in those languages is more efficient, is more performant, is faster, much faster. And so you might think that that's because CumSum is an inherently a faster function than writing a for loop, but that's not correct. In Julia, it's just as efficient to write a for loop yourself. And CumSum is basically just another way, approximately at least, of writing a for loop yourself. And so what's happening is that in those other languages, it's not that CumSum is fast, it's actually that for loops are slow. And so basically those languages are just preventing you from doing the natural thing, which would be to write a for loop, and then forcing you to use this sort of other way of thinking about this this process to use this function, because that function is actually implemented in C code, is not implemented in Python or MATLAB at all. Whereas in Julia, this is just all implemented in Julia. Sorry?
Yeah, in those languages, but in Julia.
In those languages. In Julia, this is just writing out a for loop, effectively, that you could write yourself, right? So I could have written a function, my CumSum of some data. Let's call it V, a vector. What do I need? I need a new vector that's going to be, let's say, the same length as V. And so I could do that by making sort of new V equals similar of V. So that makes a new copy of a new vector with the same length and type as V. And then I'm going to do a for loop for I in 1 to the length of V. New V number I is going to be, right, so the first one I need to start off at the start. New V at 1 is just the same as V at 1. And then from 2 to the end, 2 to the length of V, I'm going to do new VI equals new V at I minus 1 plus V at I. Return new V. And that will, so that should give me the same thing. So let's just check that. This is all unprepared, so so I'm going to do CumSum of steps and my CumSum of steps. Those should give the same result. They do. That's great. So my logic seems to be right. I just did a test of my logic. Actually, by the way, there is a module in Julia called test with a capital T, which enables you to do these kind of unit tests. And so you can just write at test, is my CumSum of steps equal to CumSum of steps? And it will run that test and it will tell you that, oh yes, that test passed, right? So you can actually sort of add these tests to your code to make sure that, suppose I now modify this in some way. So I start with 100 by mistake. Well, when I rerun the test, it will now tell me that the test failed. There was an error, and it should tell me actually where that test is that failed. In this case, it's not telling me that. I think that's to do with Pluto. But when I put it back, Pluto will rerun, and now the test passes. And so this is a great way to make sure that once you have some code and you want to refactor it or modify it in some way, you should write tests that tell you when you rerun the code with those tests, is the code still working in the same way? Okay, and so now what we need to do is test the performance. So I'm going to load the benchmark tools package, and then I'm going to do at b time of cumsum of steps, and you need this dollars. Actually, I didn't mention that last time when we looked at b time. And then we need with terminal do, because we're inside Pluto, to print out the result in here instead of in the terminal, to display this timing information in Pluto instead of in the terminal that I ran it from. So cumsum, the built-in Julia one, takes 66 nanoseconds, and now the moment of truth, what does my cumsum take? And let's see. So it's almost the same speed, right? So
I mean, I'd be more interested if you did something a lot larger, like 10,000.
Okay, sure. So let's say cool steps. Oh, just change steps. Yeah.
Yeah.
Well, let's just do steps 2. So steps 2 is a round of -1 with 10,000. That's 10 to the power 4 elements. And then let's do Julia's built-in cumsum with steps 2. How long does that take? And then how long does my cumsum take? So the point is, this is so easy to write in Julia. This is exactly the code, once you've understood what cumsum is doing, this is exactly the code that you would write.
I just like looking at cumsum. I mean, I know what it is. It's sort of like a higher level of abstraction.
Yeah, it's a high level of abstraction, and that's very important to have, definitely. So Julia's cumsum took this amount of time. So what is these two allocations? It's actually making the array, right? The similar command makes a new array. And you can see that actually my cumsum is much slower than Julia's built-in one. And you might think, oh, that's because you were using a for loop. And no, it's actually because I need to annotate this line, right? So Julia.
Don't you need the SIMD or something?
Right. So Julia, by default, has bounds checks on arrays. So when you do something like v square brackets I, you're extracting this element number I from v, and but Julia will actually, if I do steps of 11, it will actually tell me that I'm out of bounds. So it's doing a check every time I access this element. Are you in bounds or not? Are you accessing an element that actually exists in your array or not? And so I actually want to turn that off if I write a function like this, because I don't need it. If I write the function correctly, I can guarantee that I'm always in bounds.
And so dangerous if you're
annotation. Sorry?
Dangerous, right? Let's give people warnings here.
Yeah, this is dangerous. Yeah. At inbound is dangerous because, I'm having to guarantee myself that I'm not stepping outside the bounds. Julia's not going to do the work for me anymore. That's why I have to explicitly turn it off. So this is turns off bounds checks, right? So at inbounds turns off bounds checks, and this is dangerous. Okay, so when I do that and I rerun my my benchmark, what happens is that it's actually now apparently, so I think, yeah, it's basically the same, it takes the same time, right? So that is showing that a for loop in Julia, as long as you include this bounds check, turning off the bounds check, which is what cumsum is doing internally, then you will actually get the same speed. So that's a proof that for loops and this higher level construct in Julia are equally fast. Okay. If you go and look at the code for cumsum, you probably will find that it's actually a bit complicated because it's trying to deal with cases where you have a higher dimension array like a matrix. I mean, I don't think I actually want to do that right now. Okay, so to finish, today's lecture, let's look at a different way of thinking about these random walks. So far we've been drawing trajectories of random walks, and actually let's.
I don't think you've drawn. Oh, you did draw one trajectory. Okay.
I drew one trajectory, so let's draw some more trajectories. So
you definitely didn't draw trajectories today.
So let's just. I'm not sure why it's taking quite so long. Oh, because it's rerunning these benchmarks every time. Let's just comment these out. Okay, so I'm going to just rerun this a few times and we'll see some different trajectories. So let's actually add some limits on y, going from -10 to 10, say. Not sure, it's still taking a long time. Why is that? It's still rerunning these things because I didn't evaluate the cells, apologies. Okay, so now it should be fast. So there we go, okay. So there we have a sequence of different random walk trajectories. All starting at 0, and some of them go off the end because I didn't put enough space on my axes.
But by the way, I'm sort of. By the way, can we make the circles smaller, a little smaller? But I want to make a point. Yeah, that's much better actually. The idea that a trajectory is a random object, just like a number is a random object, might be worth shouting out a little bit, right? That the random object is no longer one number, right? It's an entire trajectory. It's practically a function, right? Like I could look at the value of 25 or something.
Exactly. Yeah, exactly. We are generating, in some sense, random functions. And if I generate, if I make the length a bit longer and expand my y limit again, then you can see that it actually starts looking much more like a sort of stock price, like we were talking about last time. And let's even go to 10,000, and let's make these, yeah. Something like that. Now we really have, it's sort of literally, you can think of that as a function, from 0 to 10,000, and it's sort of really a random continuous function. And you really can't think of these things like that. We're basically sampling from a set of random functions with certain properties, a certain probability distribution, actually, right? So what we really want to know is, what is the probability distribution of these sort of random paths, random functions, or So if you
I don't know if it's mind-blowing to realize that a trajectory is a random object with a probability of its own or not. But
right, it's definitely mind-blowing to me. Yeah. So for example, if we fix our attention at, in this case, time 2,500, just look at this vertical line, this grid line here, and let's generate some paths. Okay, maybe 10,000 is too many, it's too slow. Let's go back to 100. Okay, so let's fix our attention at time 25 and just regenerate. That's not a good idea, because, sorry, my limits are too. There we go. Okay, fix our attention at time 25 and ask, well, where is the random walk at time 25? You see that it dances around, right? At this particular point. Let's actually maybe add that in. So we'll just do a scatter at 25 and steps 25. And we'll color that in red. And I didn't quite get it right. It's steps 24. No.
It's cube sum of steps.
Cube sum of steps, sorry. Yes, cube sum of steps.
That's the trajectory.
There we go. Okay, so that's the one we're going to look at. As
we actually put like the title to be the value of cube steps of 24, so we can actually see the number?
Sure. There we go. So it's the position at time 25.
Equals. Yeah, or colon. Okay.
equals.
Or colon. Colon's fine.
Okay, so now let's regenerate them again. And so you see that this point is dancing around. And now we want to ask, well, what is the probability distribution of that position?
So that red point is now a random number, right? Taken from the random trajectory.
Exactly.
It's a random number.
Right. That is a random number at time 25. And so we can ask, what is the distribution of that random number?
And clearly an even number. Just you could try it a few times, or you could think about why that's true.
Yeah,
it will certainly be an even
a good point. Yeah, if you look at the value that's coming out, it's always even.
Right, because it's the result of 24 plus ones or minus ones, right? 24 odd numbers.
Right. So there's a parity argument going on. Yeah. So we can ask, what is the probability distribution of that thing? And so what is that thing, that value, that height? It's, as Alan said, the sum of 24 plus ones or minus ones. And so we actually saw what happens when you add random variables and many random variables together a few lectures ago. What we expect to happen is that we get something that is close to a Gaussian distribution, a normal distribution. And so we should expect the position at time 25 to be something like a normal distribution. Okay, now if I repeated that same experiment at time 50, well, I would see a different distribution, because at time 50, I might expect to have gone a bit further away from the origin than at time 25. So here I'm going to get a different distribution that also should look something like a Gaussian distribution or a normal distribution. And I can do that actually at all of these times in between.
Well, let's think about that a second, just before we do anything, right? The mean of that distribution is sort of, I guess, obvious, I think.
Right.
And I guess I would expect since at 50, I figure it could go, it's wider, right? It can go further than 25. I guess I expect the variance to go up in some way.
Yeah, exactly. Good point. Yeah, so this is probably, we're going to, if you sort of try now to fix your attention on 50 when I generate some new samples. Hello. Maybe it's wiggling around more than the 25 is wiggling around. So can we characterize, can we quantify all of these qualitative arguments? That's what we're going to try and do. So we could literally take, literally generate a lot of paths and literally calculate these distributions. We could do that, or we could use a different approach, which is what we're going to do. So what's the different approach? We're actually going to think about, well, if I have the probability distribution at some time, how can I get from that probability distribution to the probability distribution at the next time? So let's call Pi, P sub I, P with a subscript I and a superscript T. So I'm going to use T for the time so that it's easier to understand. So I'm going to call that the probability that ST, which is the position of the random at time T, the probability that that thing is equal to I. So I is the position that we were just drawing, and T is the horizontal time.
If T was just 25, we were focusing on T equals 25.
Exactly. So
right? And we're wondering, and I said that I has to be even or else the probability is 0.
Right. Exactly. So So S25, we wanted to know, well, how likely is it that S25 takes on the value 10, for example? So how likely is it that it takes on the value 9? It has probability 0 because it's always even. How likely is it to take on the value 10? It's some number that we want to calculate. And the sum of all of those numbers over all the values of I, over all the possible endpoint positions at time 25, has to be equal to 1. It has to be somewhere. Okay, so but we
I have to figure out, like, if I'm tossing 24 coins and getting +1 or -1, what is the chance that I'm going to add up to 10?
Exactly. Yeah.
Okay.
So that's, yeah, exactly. So let's collect all of those values together, all of those probabilities for different values of I. That should, as I said, sum up to 1. And that collection of probabilities for all the possible heights is a vector, actually. So let's call it the vector boldface P at time T. This is not a power, it's just a label saying that it's at time T.
I could be negative.
Yeah,
right?
so
Vector that goes.
These vectors have a weird indexing. They can go from sort of -10 to +10 or something. Yeah, the value of I, thanks. So what happens at the next time step, T+1? Well, at the next time step, if we were to take the histograms, we would get a different probability distribution, which is called, P vector t plus 1. So how are those two vectors actually related? Well, if you think about it, let's fix our attention on 25 on position, and not on 25, sorry. Let's fix our attention on height 10 at time t plus 1, right? So, and the question is, that's not right. Yeah, well, let's say that, yeah. So how could I arrive at position 10 at time 25, for example? Well, I had to have been at position 9 or position 11 at the previous time 24. And then I had to jump from those positions in the correct direction. So basically I have however much the probability was at that point times the probability that it jumps in the correct direction. So that I can write down in this very compact formula. So what does this say? It just says in a formula, what I just said in words, the probability that I'm at position I at the next time step, t plus 1, well, I had to be at the previous time step, t, I had to be at position I minus 1, and then jump towards position I, which I'm due with probability a half, or plus is or, I had to be at position I plus 1 and jump towards position I, so backwards. And that also happens with probability a half. So this is a formula that tells me if I know what the probabilities are, the vector of all the probabilities at time t, how I get the new vector of probabilities at time t plus 1. So it's telling me how these probability vectors evolve in time. And this equation is often called, so it's a time evolution equation, in discrete time and discrete space. And it's often called the master equation, which is a really terrible name, but that's often what it's called. I think that dates from the 30s or something. And as I said, it describes this time evolution of probabilities. And so if you think about it, what is this doing? Well, it's actually rather similar to something we already saw at the beginning of the lecture, which is Pascal's triangle. This is almost exactly the same as Pascal's triangle, except for this factor of 1/2. Right? We're adding two things together from the previous row. Basically, if you think of these as rows, or I guess they were columns, if you think of them as columns and you rotate your head, now they're rows, but basically each column you get from the previous column by applying the same kind of convolution that we applied in Pascal's triangle, except now we also are missing the one at position I, right? So before we took the one just above and the one to the left of that. Now we're taking one to the left and one to the right, and we're missing out the one in the middle, actually. It's almost the same. So there's another convolution. And so these probabilities are actually evolving just like the rows of Pascal's triangle. Okay, so we can implement that in Julia. So for example, let's write a function called evolve, which just does this calculation. So here's the calculation. So again, we're supposing that we have a vector of probabilities at some time, and we're going to make a new vector of probabilities with, again, this similar function. And then we're going to loop through all of the whole system and do this rule that I just wrote down. So the time, the probability at position I, the new time, is a half of this sum, this convolution. We could write that as a convolution. But then, just like we did in images, we have an issue, a problem, which is what to do at the boundaries. So what happens at the boundaries if some probability wants to jump, or if your random walk, thinking about the random walk, if you're actually going to fix some boundaries of the system? Why do we need to do that now? Because we're actually talking about the probability of being at each point in space, and we can only store a finite number of them. So we actually have to impose some limit on the size of the system. And then we have to worry, once we've imposed that limit, when we were simulating trajectories of a random walk, we didn't have any such limit because it could just wander off as far as it went. But now we're actually trying to store information at each of those points. We really need to stop and say, oh, you can only go up to this distance. And then we have a problem with the boundaries. And so we need to decide what the random walk will do when it hits the boundaries. So it could do different things. It could bounce off and come back. It could go around and sort of jump off one side of the system and come back on the other side. That's called a periodic boundary. When it bounces off, it's called a reflecting boundary. And what we're doing here is called an absorbing boundary. So we're just setting the value there to 0, the value of the probability. And that actually corresponds to probability leaking out of the system. So when any probability or random walk that hits the edge just disappears, just vanishes into sort of an infinite sea. You can think of my system being in contact with the sea, and I'm thinking of this random walk as heat moving around, and when it hits the sea, it just sort of dissipates into the ocean. And
the point is your sum of probabilities will no longer be 1.
Right. So this has the weird property that the sum is no longer 1, because some of your probability, a part of your probability leaked out of the system.
Right. I mean, you could think of it as like the piece that, the remainder that would bring you to 1 is now like the probability of being in the sea.
Yeah, that's the probability. Exactly. You have some probability that by this time you have already escaped. And that probability adds up to all the other probabilities to give you 1. And so, yeah, as I said, this is just a convolution. Now the kernel looks like this. You could write it like that. Okay, we've done the probability, the boundary conditions. Now we have another thing, which is the initial condition. What is the initial distribution? Where do these random walks start? Or what is the probability that they start at different places? So if they all start at position 0 at time 1, then the probability of being at position 0 is 1. Everything is there with certainty. And the probability of them being anywhere else at any other site I is 0. It's impossible. And so we just set up an initial condition that looks like that. So we can just call this function initial condition with 10, let's say 11 positions, and you see that there's a 1 in the middle and zeros everywhere else. And then, so now we can just run the time evolution. And so in order to do that, here's a function that does that. So what are we doing? We're passing in an initial vector P0, which is the probability distribution at time 0. And then I'm making a vector that contains that object. So that is actually going to be a vector of vectors, right? So if I have sort of P0 is initial condition with 11 cells. I already have a P0 somewhere else. Here, sorry. Yeah, so there's P0. That's the initial condition. In this case, I put 101 cells. And it's taking ages to run.
Hey, maybe I'll just point out that your microcentury is sort of coming to an end.
Yeah. So if I put square brackets of P0, I actually get a vector. And inside that vector, it has just one element, which is itself a vector. So that is what I meant by a vector of vectors, a vector containing vectors. And then, so let's run this time evolution. And what I'm going to get back is a vector of vectors where the vector the vector element number 4, for example, is the probability distribution of random walks at time 4. Then I can visualize that in various ways.
I would jump to the 3D visual at this point, if you don't mind.
Okay, yeah. So here's just, this is the time evolution of the histogram. Spreading out. So this is a spreading process, and then we can show this in 3 dimensions. So here we have time on this axis. So we're starting with everything at position 1, and then you see that it's spreading out over time as we go along. And we can also see that with the random walk trajectory, which is this line on the bottom. And every time I generate a new trajectory, you can see how it moves around. And so these bars are actually telling me how likely it is for this blue dot to be in each of these positions. Okay, so that's the, so what do we see?
You want to run a few more random walks just so people could see it before getting to the final end? It's kind of fun to watch that move around.
If you fix your attention, for example, on this blue dot, you should see that it visits different sites with these proportional to these probabilities. So it's very unlikely to be kind of far away, and it's very likely to end up in, not very likely, but it's more likely to end up in the middle, sorry. So hopefully that visualization makes it kind of clear in what way, what does it mean to have a probability distribution, right? We're drawing each of these histograms at that time is a probability distribution for the position of the random walker at that time, and averaged over all of these paths, and then we have a probability distribution for each position.
And I hope people actually could see that there's Pascal's triangle is basically there in the sense of, that, I mean, if you want to think of this as 1 and 1, 1, literally divided by 2, so it's half, half, and this is 1, 2, 1.
Sorry.
right, divided by 4, right? And this
Right.
is 1331 divided by 8, right? And if you recognize those numbers, and that
Exactly.
continues down. And so
Yeah.
this is in some sense a kind of picture of Pascal's triangle, normalized by 2 to the n in each row.
Right. Exactly. Yeah. Okay. So random walks are, as we said last time, very important and very interesting, and actually contain a lot of beautiful mathematics. So like Pascal's triangle comes back to suddenly without us kind of expecting it. And yeah, so there'll be some more questions about that in the homeworks.
Yeah, I guess we'll do discrete and continuous next time. I have some fun stuff to say, but
Yeah.
that'll have to wait till Wednesday's lecture.
Yeah. Okay. So see you all next time.